Assalamu alaikum. Welcome back to the lecture series for operating systems. How are you? Getting back into the groove of studying? I hope you're doing well. Let's start lecture 4. We are continuing the chapter called Processes. Please refer to the third chapter of the William Stallings book for this topic. Let us look at the things we learned in the last lecture. In the last lecture, we understood the process image. We talked about the process control block. We understood the data structures the OS uses to manage processes. We realized the role of the PCB in an operating system. Now let us talk about the mechanisms that an OS uses for process control. Process control means making the user processes execute under a set of rules dictated by the operating system, ensuring the execution of all processes and preventing chaos in the system. Let me reiterate a concept that I discussed with you in the very first lecture when we were looking at the evolution of operating systems. I told you that the processor has at least two modes of execution, the kernel mode and the user mode. The kernel mode is also called the system mode or the control mode or the supervisor mode. Privileged instructions are instructions that can only be executed in the kernel mode. All other instructions are called user instructions. Privileged instructions include those that read or alter a control register, like the PSW, primitive IO instructions, and the instructions relevant to memory management. We do not want the user programs to change the eFlags register. If user programs change the condition codes, the system will not function properly. We also do not want the user process to be able to use the IO device on its own without operating system intervention. If the OS is already using the device, the user process can interfere with the OS's operation, and this can create chaos in the system. We also do not want user processes to be able to allocate main memory on their own without OS intervention. If they do so, a user process can allocate a memory location for itself when it is already allocated by the operating system to someone else. The whole concept of system management will collapse if user processes are able to bypass the OS. The OS is the god of the system. Suppose you are a process. Then whatever you want, you ask the god of the system to grant it to you. The OS has complete control over all resources in the system, and this control must never be challenged. Hence the need for kernel mode and privileged instructions. OS executes in the kernel mode. All applications run in the user mode. OS is the only entity that can execute privileged instructions. The kernel of the OS is the portion of the OS encompassing the most important system functions. Most of the time, the kernel of an OS is brought into the RAM when system is booted and stays in the RAM as long as the system runs. So in many operating systems, the kernel is also called the resident part of the OS because it is never swapped out to the disk. You may have heard people say that such and such OS is heavy. What they are implying is that the OS takes up a lot of space in the RAM And this is mostly because the resident part of the OS is large. Typical functions of an operating system kernel are listed in this table. Process management, process creation and termination, process scheduling and dispatching, process switching, process synchronization and support for inter-process communication, management of process control blocks, memory management, allocation of address space to processes, swapping, page and segment management, I/O management, buffer management, allocation of I/O channels and devices to processes, support functions, interrupt handling, accounting, and monitoring. I am not going to talk about these functions in detail because they will be covered in the chapters of this course. The first question that arises is how does a processor know which mode it is executing in, or how is the processor's mode determined? There is a bit in the program status word which when reset means the processor is working in one mode, and when set means the processor is working in the other mode. Changing this bit clearly means changing the mode of the processor. A change in the mode of the processor from user to kernel or from kernel to user is called a mode switch. A mode switch happens in response to certain events, and we will look at them shortly. Look at the instruction cycle. When it starts, an instruction is fetched from the memory address which is in the program counter. Then the instruction is decoded and executed. If the system accommodates interrupts, then after execution of an instruction, the processor will check its interrupt pins for a pending signal. If there is no interrupt signal, it fetches the next instruction. If an interrupt signal is pending, the processor loads the address of an interrupt handler routine in the program counter. Then it switches from user mode to kernel mode. You must understand that the interrupt handler is part of the operating system and it may want to execute a privileged instruction. So, kernel mode must be set up. Now the instruction fetched is the first instruction of the interrupt handler, and we say that control has been transferred to the interrupt handler. Now I am leaving the topic of mode switch and coming back to the star of this chapter, the process. Remember we talked about the reasons for process creation? Well, students, the time has come to talk about steps involved in process creation. Number 1. Assign a unique identifier to the new process. A new entry is added to the primary process table. If you want to revise what the primary process table is, go to the lecture dealing with process description. Number 2. Allocate space for the process. This means space is to be allocated for all four components of the process image: program, data, stack, and PCB. 3. Initialize the PCB. Set up the initial values. Store the process ID, user ID, parent ID. Initialize processor state information. store its state as ready or ready suspended, give it a priority level. If it inherits some resources from its parent, store their IDs in resource utilization portion. Store pointers to the process pages in memory management portion. Number 4. Set the appropriate linkages. If the OS maintains its queues in linked lists, then the process must be inserted into the ready or ready suspend queue as a node of this linked list. If it implements queues as arrays, the process must be inserted in the appropriate array. Actually, a pointer to the PCB of the process is inserted in any queue and it represents the whole process. Number 5. Create or expand other data structures. The OS may be keeping track of resource and memory utilization of all processes. If so, it will be maintaining tables in which it would have an entry for each process in the system. Now that a new process has been added to the system, the OS has to make an entry in each of these tables for it. When control is transferred from a user process to another user process due to some reason, this is called a process switch. Assume process A is currently running. Due to any reason, the execution of process A is paused and the processor is taken away from it, and then it is given to another process called B. This is a process switch from A to B. The entity taking the process away from process A is the operating system. The entity giving the processor to process B is the operating system too. This means that a process switch comprises transfer of control from the running process to the OS, transfer of control from the OS to another process. Since it is necessary that the OS gets involved, we loosely define the process switch as transfer of the processor from one process to another. A process switch may occur anytime the OS regains control of the processor from the running process. The table shown here lists three mechanisms that interrupt a process. One is the interrupt, the other is called a trap, and the third is a supervisor call. We discuss them individually in the following slides. Before we go any further, let me remark that system interrupts are of two types: the ordinary interrupt and the trap. The ordinary interrupt is generated due to an event that is external to and independent of the currently running process. The running process has not generated the interrupt. The interrupt has occurred due to something other than the running process. There are three kinds of the ordinary interrupt: clock interrupt, IO interrupt, and memory fault. I will talk about these in detail, but let us first consider what happens when an ordinary interrupt occurs. The processor is taken away from the running process. A generic interrupt handler routine, which is a part of the OS, starts to execute. It does some basic housekeeping, like changing the user mode of the processor to kernel mode, as a user process is no longer running now. The OS is running. The generic interrupt handler transfers control to an OS routine that is concerned with this interrupt. The interrupt specific routine completes and passes control to the operating system. So far, a process switch has not happened. Why? Because control is still with the operating system. The operating system may pass control to the interrupted process or to a different process. If the OS passes control back to the process that was interrupted, then no process switch takes place. We took the processor from the running process momentarily and then we gave the processor back to the running process. But if the OS passes control to the dispatcher and the dispatcher passes control to some other process than the one interrupted, then we have just witnessed a process switch. Let's talk about the clock interrupt. This interrupt comes from the clock, indicating that the time slot of the running process has expired. After the clock interrupt, control passes from the running process to the interrupt handler. The interrupt handler passes control on to the dispatcher. The dispatcher selects a process from the ready queue. The selected process starts execution on the processor. So what does this mean? This means that every clock interrupt leads to a process switch. The expiry of the time slot means the running process must be removed from the processor and another process must be granted access. The I/O interrupt comes from an I/O device indicating that the I/O action it was performing is complete. After the I/O interrupt, control passes from the running process to the interrupt handler. The interrupt handler passes control on to the operating system. The operating system identifies processes which are waiting for this event. These processes will be found either in the blocked or the blocked suspend queue. The operating system moves the waiting processes into appropriate queues. If the waiting process is in the blocked queue, it is moved to the ready queue. If the waiting process is in the blocked suspend queue, it is moved to the ready suspend queue. The OS determines if a process higher in priority than the interrupted process has been added to the ready or ready suspend queues. Suppose that this is true. If the higher priority process is in ready suspend queue, it must be brought into memory and moved to the ready queue. Once this is done, the higher priority process is selected by the dispatcher from the ready queue and control is transferred to it. In this way, a process switch occurs. If no higher priority process has been added to the ready or ready suspend queues, control is passed back to the interrupted process because it has the highest priority. An I/O interrupt may or may not lead to a process switch. Alright students, now it's time for the tasks. Pause the video, open a Word document, name it according to the format shown here, and then write the answers of these tasks in the Word file. Task number 1. Can you think of a scenario where a clock interrupt does not lead to a process switch? Task number 2. Can an I/O interrupt be related in any way to the running process. A memory fault indicates that the address for which the processor has generated a memory reference is not loaded in main memory. Instead, it is present on the hard disk. It is also called a page fault. When the processor wants instruction or data, it generates a memory reference. If virtual memory is employed, the memory reference generated may be of main memory or the hard disk. If the memory reference maps to the hard disk, this is a memory fault. After the memory fault, control passes from the running process to the memory management part of the OS, which issues an IO request to bring the page or segment containing the desired address into main memory. Recall that a page or segment is a chunk of the process image. If virtual memory uses pages, all chunks have the same size. If it uses segments, each chunk has a different size. The interrupted process is moved to the blocked queue. It will remain blocked as long as the IO request is not complete. Once the page containing the desired word has been brought in, this process will be moved from blocked to the ready queue. The operating system passes control on to the dispatcher. The dispatcher selects a process from the ready queue. The selected process starts execution on the processor. So this means that every memory fault leads to a process switch. Some people might ask how a memory fault is external to and independent of the currently running process. The memory fault is generated when the processor asks for a piece of data not loaded in main memory. There is no bug or error in the code of the running process. This happens because we partially load processes in main memory as we do not have enough space in the RAM. So it is the fault of the memory management system, not the running process. If the running process is run in a different virtual memory environment or in the same environment with a different number of processes, the memory fault may not occur, or it may happen that a memory fault for a different word occurs. This shows that memory faults occur due to the system state and not because of the running process. A trap is a system interrupt that occurs because of an error or an exception condition generated within the currently running process. As an example, consider that the running process tries to access a file that it should not. This is illegal file access. Some of you who remember the reasons for process termination might say that the running process must be terminated. First, I want to tell all such students that I am proud of them for remembering this. And you can email me and tell me if you are one of them. No lying, mind you. Then I ask you to remember I told you that it is not necessary a reason for process termination leads to termination. It is up to the OS designer to decide if he wants to handle an erroneous condition or violation amicably, or if it is so disturbing to his system that he would rather kill the misbehaving process. We discussed a long list of reasons for process termination, but an OS designer might consider only 2 or 3 reasons big enough to result in the murder of the criminal process. So let us return to our problem. A process tries to access a file it isn't supposed to access. A trap occurs. The difference between an ordinary interrupt and a trap must be clear to you. Trap occurs due to something the running process did. The OS determines whether the error or exception condition is fatal. If the error or exception condition is one of the reasons of process termination in this OS, the interrupted process is moved to the exit state. The OS transfers control to the dispatcher. The dispatcher selects a process from the ready queue. The selected process starts execution on the processor, and a process switch has just occurred. If the error or exception condition is not fatal, the succeeding actions will vary according to operating system and error. The OS may attempt recovery, or it may simply notify the user. Have you ever seen a message box telling you that there seems to be an error in the application and asking you to close it or restart it? That is the operating system notifying you that I cannot pull us out of this mess. You do something. If the OS can recover from the error, or the user helps to recover from the error, the OS may resume the running process. If recovery is not possible, the OS might do a process switch. So we can conclude that a trap may or may not lead to a process switch. The running process calls a function of the operating system. This is called a supervisor call or an operating system service call. For example, the running process requires a file to be brought into RAM from secondary storage. This is an IO transfer, and the running process is making an IO request. The running process relinquishes the processor and control passes to the operating system. The operating system directs the relevant module to complete the request made by the process. In our example, the OS directs the hard disk driver to start IO transfer of the requested file from hard disk to RAM. If the process request will take time to complete, the process is placed in the blocked queue. The OS transfers control to the dispatcher. The dispatcher selects a process from the ready queue. The selected process starts execution on the processor. Tada! A process switch has just occurred. If the process request can be readily satisfied, the OS resumes the process who made the supervisor call. Now, what we see is most supervisor calls result in process switching. This happens because most requests take time to complete. If someone claims that every supervisor call leads to a process switch, I will not say that he is wrong. But we must understand that I am letting his statement go unchecked because it is correct 99% of the time. Still, there is a chance that a supervisor call does not lead to a process switch. Two more tasks for you. Task number 3. A memory fault occurs. The address space of the running process has no room for the incoming page. What will you do? Task number 4. When I click New, then blank document in Microsoft Word, the running process makes a supervisor call. What is it asking the operating system to do? See you on the other side. So far, we have understood what a process switch is. Then we investigated the events that lead to process switch. Now let us look at the process switch and see what happens inside it. Steps of process switch. Save the context of the processor, including program counter and other registers. Variable values in the processor's registers are saved to the data portion of the process image. The program counter and condition codes are saved in the PCB. Update the PCB of the running process. This includes changing its state from running to an appropriate state. The reason for leaving execution and accounting information will also be recorded in the PCB. Accounting means keeping track of statistics like processor cycles used, memory locations used, etc. So far, we understood what a process switch is. Then we investigated the events that lead to process switch. Now, let us look at the process switch and see what happens inside it. Steps of process switch. Save the context of the processor, including program counter and other registers. Variable values in the processor's registers are saved to the data portion of the process image. The program counter and condition codes are saved in the PCB. Update the PCB of the running process. This includes changing its state from running to an appropriate state. The reason for leaving execution and accounting information will also be recorded in the PCB. Accounting means keeping track of statistics like processor cycles used, memory locations used, etc. Move the PCB to the appropriate queue. Select another process for execution. Update the PCB of the selected process. This includes changing its state from ready to running. Update memory management data structures. The OS might change memory allocation of the interrupted or the selected process or both. It might completely kick the interrupted process out of main memory. It might trim or decrease the space allocated to the interrupted process. It might increase the space allocated for the selected process. And these changes will lead to change in memory tables. Restore the context of the selected process to that which existed when it was switched out last time. This means loading the values of the program counter and registers that were stored in its PCB when it was switched out. Let us zoom into the process switch. Let's just look at the start of the process switch. If an interrupt signal is pending, a trap has occurred, or a supervisor call is made, the program counter is adjusted to the address of an operating system function or module. The processor switches from user mode to kernel mode. The context of the running process is saved from the processor's registers into its PCB. Let us continue to zoom into the process switch. Just now we started a process switch. Now we are ending the same process switch. The context of the selected process is restored from its PCB into the processor's registers. The processor switches from kernel mode to user mode. The program counter is adjusted to the address of the instruction of the selected program to be executed next. But some people would be asking, what is this context? What is the context of the process that you are restoring and that you are saving? Let's answer this question. The portion of the PCB referred to as processor state information constitutes the context of the process. Processor state information includes program counter, processor's registers, and stack information. The context of the process is saved in the PCB when switched out. The context of the process is restored on the processor when switched in. Saving and restoring the context allows a process to pick up its execution from the point at which it was interrupted. A process switch is therefore the changing of user processes on the processor. The processor is stopping execution of one user process and committing itself to another. A mode switch is the changing of execution mode of the processor. If the change is from user to kernel mode, privileged instructions will be able to execute. If it is the opposite change, it will hinder the executing process from running privileged instructions. Every process switch incorporates two mode switches. If you go back to the two slides where I described the start and end of a process switch, you will see there is a mode switch in the starting part and there is another mode switch in the ending part. A mode switch may or may not be a part of events that lead to process switch. Mode switches may happen, and after the switch, the OS might decide to resume the process that was running previously. So the occurrence of a mode switch does not guarantee a process switch. On the other hand, the occurrence of a process switch guarantees two mode switches. So, in this lecture, we understood how processes are controlled. We talked about the process switch and the events that may lead to it. We understood the mode switch. We tied the two switches together and saw how they happen in an operating system. As always, I will leave you with a few things to do, and the things to do are also the same. You are supposed to read the book, and you are supposed to save the Word file in which you were writing the answers to the tasks. You've already seen how I have asked you to submit them via Google Classroom, and I'll do that again for this task file as well. Write your questions on a piece of paper and keep it in front of you during the online session. And if you have any suggestions relevant to content or quality of this lecture, email them to me. I'll see you soon, students. Take care. I love you all. Allah Hafiz.